Hello, dear friend, and welcome to this quiet corner of history. Tonight, we set aside the noise of the present and wander gently into the stories of the past. Whether you're curled up beneath the blankets, resting after a long day, or simply seeking calm company for your evening, I'm grateful you've chosen to be here. If you'd like, share in the comments where in the world you're listening from. I always love seeing how far this community stretches across time zones and continents. And if these soothing journeys through history bring you comfort, consider subscribing so we can meet again. For now, let's loosen the weight of the modern world and step softly into the echoes of yesterday. Close your eyes and let yourself drift back through the mists of time, to a world where the line between dream and reality was as thin as morning fog over the Aegean Sea. Tonight, we journey together into a different kind of story, not of gods and heroes, but of mortals who discovered something that would forever alter the fabric of human existence. This is the story of how the nuclear bomb came to be, and how its terrible light transformed everything we thought we knew about power, about war, about the very nature of human civilization itself. Picture, if you will, the world as it was in the earliest years of the 20th century, a world that still belonged, in many ways, to the 19th. The great cities of Europe glowed with gaslight and the new electric lamps, their streets crowded with horse-drawn carriages alongside the occasional sputtering automobile. In laboratories and universities across the continent, scientists worked with glass tubes and copper wires, with microscopes and spectroscopes, peering into the hidden architecture of matter itself, unaware that they stood at the threshold of revelations that would shake the foundations of reality. The story begins, as so many great transformations do, not with a single dramatic moment but with quiet accumulations of knowledge, with patient observations made in dim rooms where dedicated souls sought to understand the fundamental nature of existence. In these years, physics was experiencing what we might call a golden age of discovery, though those living through it could not have known how golden, how world-changing, their findings would prove to be. Consider the element uranium, discovered in the dying years of the 18th century and named for the planet Uranus, which had itself been discovered only years before. For decades, uranium was considered merely an interesting curiosity, a dense metallic element with few practical applications beyond adding a greenish tint to glass and ceramics. Uranium glass, with its faint glow under certain lights, was fashionable for a time in Victorian drawing rooms, decorative pieces that held within their atoms secrets that would have astonished their owners. But in the winter of 1896, a French physicist named Henri Becquerel made an observation that would open a door into a realm previously unimagined. Becquerel was studying phosphorescence, the tendency of certain materials to glow after being exposed to light. He had placed uranium salts on photographic plates wrapped in thick black paper and set them in sunlight, expecting to find that the uranium would glow and expose the plates through the paper. But when clouds obscured Paris for several days and Becquerel developed the plates anyway, expecting to find them blank, he discovered instead that they had been strongly exposed, as if by invisible light that required no sun to activate it. Uranium, it seemed, was spontaneously emitting some form of radiation, an energy that came from within the substance itself, requiring no external source to trigger it. This was radioactivity, though the word had not yet been invented. The discovery suggested that atoms, which were thought to be the indivisible, eternal building blocks of matter, were not unchanging after all, but could transform themselves, releasing energy in the process. Into this mystery stepped Marie Curie, a young Polish scientist working in Paris, whose determination and brilliance would help unravel the secrets of radioactivity. Working in conditions of remarkable hardship, in a converted shed that was sweltering in summer and freezing in winter, Marie and her husband Pierre processed tons of pitchblende ore, seeking to isolate the elements responsible for its intense radioactivity. The work was exhausting and dangerous. They would stir boiling vats of ore with iron rods as tall as themselves, and Marie's hands became scarred and burned from handling radioactive materials. From this labor, they isolated two new elements, polonium, named for Marie's native Poland, and radium, which glowed with its own ethereal blue light. Radium was intensely radioactive, millions of times more so than uranium, and this small vial of glowing material became almost an object of mysticism, a substance that seemed to bridge the gap between matter and energy, between the solid world and something more fundamental. Picture Marie Curie in her darkened laboratory, holding up a vial of radium that cast its ghostly luminescence across her face, illuminating her eyes with wonder and fierce intellectual curiosity. She could not have known that this beautiful glow was a visible manifestation of atomic decay, of particles being flung from unstable nuclei at tremendous speeds, or that prolonged exposure to such radiation would eventually claim her life. In those early days, scientists would carry radioactive materials in their pockets, delighting in the glow they produced, unaware of the invisible damage being done to their cells and tissue. The Curie's work earned them the Nobel Prize in 1903, shared with Becquerel, and opened up an entire new field of scientific inquiry. Radioactivity was not merely a curiosity but a window into the heart of matter itself, suggesting that atoms had internal structure, that they could change and transform, releasing enormous amounts of energy in the process. In the first decades of the 20th century, our understanding of the atom underwent a revolution. The old model, tiny, solid spheres like infinitesimal billiard balls, gave way to increasingly complex pictures. Ernest Rutherford, a New Zealand-born physicist working in England, demonstrated that atoms had a tiny, dense nucleus at their center, surrounded by orbiting electrons. The nucleus itself, he discovered, was made of protons, positively charged particles, and later, James Chadwick would discover the neutron, an uncharged particle of similar mass to the proton. Imagine the atom as Rutherford understood it, a nucleus so small that if an atom were enlarged to the size of a cathedral, the nucleus would be no larger than a fly at its center, yet containing nearly all of the atom's mass. The electrons orbited in the vast empty space around this nucleus, like planets around an impossibly distant sun. Matter, which seemed so solid, so substantial, was revealed to be mostly emptiness, with tiny concentrations of mass held together by forces we were only beginning to understand. And what forces they were. Rutherford and his colleagues discovered that the nucleus was held together by an incredibly powerful force, far stronger than the electromagnetic force that governed the behavior of electrons. This nuclear force had to be powerful indeed to overcome the natural repulsion between the positively charged protons packed into such a tiny space. When this force could be disrupted, when the nucleus could be split or fused with another nucleus, the energy released would be immense, deriving from Einstein's famous equation E=mc², which showed that mass and energy were interchangeable, and that even a tiny amount of mass contained within it enormous energy. Einstein's equation, published in 1905 as part of his theory of special relativity, seemed at first to be purely theoretical, a mathematical relationship with no practical application. The speed of light squared, 186,000 miles per second multiplied by itself, was such an enormous number that even converting a tiny amount of mass into energy would release staggering power. But there seemed no way to actually accomplish such a conversion. Mass and energy were equivalent, yes, but transforming one into the other appeared to be beyond human capability. Throughout the 1920s and 1930s, physicists continued their exploration of the atomic nucleus, accelerating particles to higher and higher energies, smashing them into various nuclei to see what would happen. It was work driven by pure curiosity, by the desire to understand the fundamental nature of reality. In laboratories across Europe, in Cambridge, in Berlin, in Paris, in Copenhagen, scientists collaborated and competed, sharing their findings in journals and at conferences, building together a picture of the subatomic world. These were years of remarkable intellectual ferment, when physics seemed to overturn all the old certainties. Quantum mechanics revealed that particles could behave like waves, that you could never know both the position and momentum of a particle with perfect precision, that observation itself affected what was being observed. The universe at its smallest scales was strange beyond imagination, governed by probabilities rather than certainties, by principles that violated common sense and yet were mathematically precise and experimentally verifiable. In this context, the discovery of nuclear fission, when it came, was both expected and shocking. Scientists had been bombarding heavy elements with neutrons for years, observing the products of these collisions, noting that sometimes the target nucleus would absorb the neutron and become a different isotope, sometimes it would emit particles and transform into a different element entirely. But in December of 1938, in Berlin, two chemists named Otto Hahn and Fritz Strassmann conducted an experiment whose results confounded them. They had bombarded uranium with neutrons and expected to create elements slightly heavier than uranium. Instead, their chemical analysis showed the presence of barium, an element with roughly half the atomic weight of uranium. It was as if they had split the uranium atom nearly in half, which seemed impossible. Surely the forces holding the nucleus together were too strong to allow such a thing. Hahn wrote to his former colleague Lise Meitner, who had fled Germany the previous summer to escape Nazi persecution. She was Jewish, and Berlin was no longer safe for her. Meitner was spending Christmas with her nephew Otto Robert Frisch in a small Swedish village, and when she received Hahn's letter, the two of them went for a walk in the snowy woods to discuss this perplexing result. Picture them there, aunt and nephew, wrapped against the cold, walking through forests where the bare branches were laden with snow, discussing atomic physics in hushed, excited tones. Meitner had a profound understanding of nuclear physics, and as they talked, the explanation became clear to her. The uranium nucleus, she realized, was like a liquid drop held together by surface tension. When it absorbed a neutron, the nucleus would begin to oscillate, deforming into an elongated shape. If the deformation became severe enough, the nucleus could split into two smaller nuclei, like a water droplet pinching in the middle and separating into two drops. Using Einstein's equation and their knowledge of nuclear masses, Meitner and Frisch calculated how much energy would be released in such a split. The two smaller nuclei together weighed slightly less than the original uranium nucleus and the absorbed neutron. That missing mass would be converted entirely into energy, about 200 million electron volts per fission, an enormous amount on the atomic scale. Frisch returned to Copenhagen and immediately conducted an experiment to test their theory. Using a uranium sample and a neutron source, he looked for the high-energy particles that would be produced if the nucleus truly split. The results confirmed it. Nuclear fission was real, and it released energy just as Meitner had predicted. The discovery sent shockwaves through the physics community. Within months, laboratories around the world had confirmed the finding. But more startling still was the discovery that uranium fission released not just energy but additional neutrons, 2 or 3 on average for each fission. These neutrons could strike other uranium nuclei, causing them to fission as well, releasing more neutrons, which could cause more fissions in a cascading chain reaction. Imagine a room full of mouse traps, each one set and balanced with a ping-pong ball on top. Throw one ball into the room, and it will trigger a trap, which will fling its ball into the air, which will trigger more traps, which will release more balls, until in the space of a few seconds the entire room erupts in a chaos of snapping traps and flying balls. This is the essence of a chain reaction, and if it could be achieved with uranium atoms, the amount of energy released would be inconceivable. Scientists quickly realized the implications. A controlled chain reaction could provide a new source of power, potentially more efficient than any chemical fuel. An uncontrolled chain reaction could create an explosion of unprecedented force. And all of this was being discovered in 1939, as the world stood on the brink of another great war. The First World War had been terrible enough: the trenches, the poison gas, the machine guns that mowed down advancing soldiers like wheat before a scythe. That war had introduced mechanized killing on an industrial scale, had shown that modern technology could make warfare more deadly than ever before. Now, barely 2 decades later, the world was sliding toward another conflict, and this time the combatants would have access to technologies far more terrible than anything seen in the First War. In Germany, Adolf Hitler had risen to power, bringing with him an ideology of racial hatred and territorial expansion. He had already swallowed Austria and Czechoslovakia, and in September of 1939, his armies would invade Poland, triggering declarations of war from Britain and France. The Nazi regime was brutal beyond measure, determined to create a new order in Europe through conquest and genocide, willing to employ any means necessary to achieve their goals. And now, German scientists had discovered nuclear fission. Germany had access to uranium supplies from Czechoslovakia. Some of the world's finest physicists were German. The possibility that Nazi Germany might develop a nuclear weapon became a terrifying prospect for those scientists who had fled the regime or who opposed its ideology from afar. In the summer of 1939, several refugee physicists in the United States, Leo Szilard, Eugene Wigner, and Edward Teller, realized they needed to alert the American government to the potential of nuclear weapons. But how to make officials understand the significance of abstract physics? How to convey the urgency of the threat when the very idea of atomic energy seemed like science fiction? They decided to approach Albert Einstein, by then the most famous scientist in the world, and ask him to write a letter to President Franklin Roosevelt. Einstein, a pacifist who had fled Germany in 1933, was deeply troubled by the prospect of nuclear weapons, but he understood the danger posed by Nazi Germany. In his modest summer cottage on Long Island, Einstein met with Szilard and dictated a letter explaining the recent discoveries in nuclear physics and warning that extremely powerful bombs based on nuclear fission might be possible. Picture that scene: Einstein in his rumpled clothes, his famous wild hair already gray, his eyes reflecting both the depth of his understanding and his sadness at what that understanding implied. The men who had given us the theory of relativity, who had shown us that space and time were woven together, that gravity was the curvature of spacetime itself, was now helping to set in motion events that would lead to the creation of the most destructive weapons humanity had ever known. The letter reached Roosevelt in October 1939. The president, preoccupied with the war beginning in Europe and America's policy of neutrality, understood enough of the implications to take action. He established an advisory committee on uranium to investigate the possibility of developing nuclear weapons. But progress was slow at first. The committee had limited funding, and many scientists were skeptical that a practical weapon could actually be built. The theoretical possibility of a chain reaction was one thing, engineering an actual bomb was quite another. For a chain reaction to occur, you needed not just any uranium but a specific isotope, uranium-235. Natural uranium is mostly uranium-238, which readily absorbs neutrons but does not fission easily. U-235, which does fission when struck by neutrons, makes up less than 1% of natural uranium. To build a bomb, you would need to separate the U-235 from the U-238, a task of enormous difficulty since the two isotopes are chemically identical and differ in mass by less than 2%. Alternatively, scientists discovered that when U-238 absorbed a neutron, it would eventually transform through radioactive decay into a new element, plutonium-239, which was also fissionable. But plutonium did not exist in nature in significant quantities. It would have to be created in nuclear reactors and then chemically separated from the uranium and other radioactive materials. Either path, uranium enrichment or plutonium production, would require industrial facilities on an unprecedented scale, would cost vast sums of money, and would need thousands of workers. It was not the sort of project that could be undertaken half-heartedly or in secret by a small group of researchers. It would require governmental commitment and resources on a massive scale. The catalyst for such commitment came on December 7, 1941, when Japanese aircraft struck the American naval base at Pearl Harbor in Hawaii, sinking battleships and killing thousands of Americans. The United States, which had been providing material support to Britain while remaining officially neutral, now entered the war directly. The conflict became truly global, with fighting across Europe, Asia, North Africa, and the Pacific. In this context of total war, the possibility of nuclear weapons took on new urgency. If such weapons could be built, they might determine the war's outcome. And if Germany built them first, the consequences could be catastrophic. In the fall of 1941, even before Pearl Harbor, the British had produced a report estimating that a practical nuclear bomb could be built with about 10 kilograms of enriched uranium and would have an explosive force equivalent to thousands of tons of TNT. Roosevelt and his advisors decided to pursue nuclear weapons development as a top priority. In August 1942, the project was placed under military control and given the code name Manhattan Engineer District, shortened to the Manhattan Project. Brigadier General Leslie Groves, who had just overseen the construction of the Pentagon, was put in charge of the project. Groves was a brilliant administrator, demanding and abrasive but capable of managing an undertaking of unprecedented complexity and scale. To direct the scientific work, Groves chose J. Robert Oppenheimer, a theoretical physicist from the University of California at Berkeley. Oppenheimer was an unusual choice in many ways. He had no Nobel Prize, no major experimental discoveries to his name, and had previously been a somewhat impractical academic more interested in Sanskrit and French poetry than in engineering. But he had a remarkable ability to understand and synthesize different areas of physics, to see connections that others missed, and most importantly, he could communicate with and inspire other scientists. Picture Oppenheimer in those early days of the project, tall and thin, almost gaunt, smoking constantly, his blue eyes intense and restless with thought. He spoke in a soft voice, often in long, complex sentences studded with literary and philosophical allusions. He could be arrogant and cutting, but also charming and deeply empathetic. Those who worked with him spoke of his ability to understand their work almost instantly, to grasp the essential problem and suggest solutions they had not considered. He was a Renaissance man in an age of increasing specialization, and the Manhattan Project would be his great test, the challenge that would reveal both his genius and his capacity for moral anguish. Oppenheimer's first task was to choose a location for the laboratory where the actual weapons would be designed and built. It needed to be isolated for security reasons, but not so remote that it could not be supplied and staffed. After surveying several sites, he chose a location in northern New Mexico, in the Jemez Mountains northwest of Santa Fe. There, on a mesa at 7,000 feet elevation, stood a boys' school called Los Alamos Ranch School. The school was acquired, its buildings repurposed, and construction began on what would become one of the most important scientific facilities in history. Meanwhile, across the country, an industrial empire was being built in secret. At Oak Ridge, Tennessee, vast facilities were constructed to enrich uranium through several different methods: electromagnetic separation, gaseous diffusion, and thermal diffusion. Each method had advantages and drawbacks, and since no one knew which would work best, all were pursued simultaneously. The Y-12 electromagnetic plant alone consumed more electricity than entire states, its thousands of magnets requiring vast amounts of copper, so much that the project borrowed silver from the U.S. Treasury to wind magnet coils when copper supplies ran short. At Hanford, Washington, reactors were built along the Columbia River to produce plutonium. These reactors used graphite as a moderator to slow down neutrons and allow a controlled chain reaction in natural uranium. The plutonium produced would then be chemically separated in massive remote-controlled facilities, since the radioactive materials were far too dangerous to handle directly. The Columbia River provided the cooling water needed to prevent the reactors from overheating, and its remoteness helped ensure secrecy. Think about the scale of what was being attempted. Cities were being built in the desert and the pine forests, cities that did not appear on maps, where tens of thousands of people worked on projects whose ultimate purpose they did not know. Workers enriched uranium without knowing what uranium was or why enrichment mattered. They operated equipment they did not understand, following procedures designed by distant scientists, all held together by security classifications and the shared sense that their work was essential to winning the war. The Manhattan Project employed at its peak more than 130,000 people and cost nearly $2 billion, equivalent to over $20 billion in today's currency. It was kept secret not just from America's enemies but from most of the American government. Few members of Congress knew of its existence. Vice President Harry Truman, who would later have to make the decision to use the weapons, only learned of the project when he became president after Roosevelt's death. At Los Alamos, meanwhile, an extraordinary community was taking shape. Oppenheimer recruited the finest scientific minds in America and Europe. Physicists, chemists, metallurgists, explosives experts, mathematicians. Many were already famous, like Enrico Fermi, who had built the first nuclear reactor in Chicago. Others would become famous through their work on the project. There was Hans Bethe, who headed the theoretical division, Richard Feynman, a brilliant young physicist known for his irreverent sense of humor, and many others whose names would become legendary in the history of physics. These scientists brought their families to Los Alamos, creating a strange hybrid of university campus and military installation. Children played in the shadow of armed guards. Parties and lectures happened in buildings where the secrets of nuclear fission were being unraveled. The scientists chafed at military security. They were used to open exchange of ideas, to publishing their findings, to the academic tradition of freely shared knowledge. Now they worked in secrecy, unable to tell even their families what they were doing, their mail censored, their movements restricted. Yet there was also an extraordinary sense of purpose and intellectual excitement. The brightest minds of a generation were gathered together, working on problems at the very edge of human knowledge. In evening seminars, they would discuss not just nuclear physics but philosophy, politics, literature. Oppenheimer himself would sometimes lecture on Hindu philosophy or recite poetry. There was a sense that they were not just building a weapon but participating in something that would reshape human history. The technical challenges were immense. Simply determining how much fissionable material would be needed for a bomb required solving equations that had never been solved before, running calculations that pushed the limits of available computing power. This was before electronic computers, so computing meant rooms full of people running mechanical calculators and solving equations by hand. They had to understand the behavior of materials under conditions that had never been studied, had to invent new instruments to measure processes that happened in millionths of a second. There were two basic designs being pursued. The simpler was called Little Boy, a gun-type weapon where one piece of enriched uranium would be fired at high speed into another piece, creating a supercritical mass that would explode. This design was relatively straightforward, and the scientists were confident enough that it would work that they would not test it before using it. The second design, codenamed Fat Man, used plutonium and an implosion mechanism. Plutonium could not be used in a gun-type weapon because it would pre-detonate, starting the chain reaction before full supercriticality was achieved. Instead, a sphere of plutonium would be surrounded by conventional high explosives. When these explosives were detonated simultaneously from all directions, they would compress the plutonium to perhaps half its normal radius, greatly increasing its density and creating the supercritical conditions needed for a massive chain reaction. Getting implosion to work required extraordinary precision. The explosive lenses, shaped charges designed to focus the blast inward, had to detonate within millionths of a second of each other. The compression had to be perfectly symmetrical, or the plutonium core would squirt out the side rather than compress evenly. It was like trying to squeeze a balloon perfectly uniformly from all directions at once, except that the balloon was made of plutonium. The squeezing happened at supersonic speeds, and any imperfection would cause the entire weapon to fail or produce only a tiny fraction of its potential yield. Throughout 1944 and into 1945, the scientists and engineers at Los Alamos worked feverishly to solve these problems. They test-fired conventional explosives in the canyons around Los Alamos, sometimes at night, the flashes visible from Santa Fe 30 miles away. They developed new forms of high explosives and new detonation systems. They studied the properties of plutonium, which turned out to be one of the most complicated metals ever encountered, with 6 different crystal structures depending on temperature and pressure. All of this was happening against the backdrop of the war in Europe and the Pacific. By early 1945, Germany was clearly losing. Allied armies were closing in from west and east, and Hitler's regime was collapsing. Intelligence suggested that the German nuclear program had never gotten far, their best physicists had fled or been persecuted, their resources had been diverted to other weapons, and they had made critical errors in their reactor designs. The original impetus for the Manhattan Project, to beat Germany to the bomb, was becoming moot. But in the Pacific, the war ground on. Japan, though clearly losing, showed no signs of surrendering. American forces were capturing island after island, each victory costly in lives and material. The invasion of Okinawa, lasting from April to June 1945, resulted in tens of thousands of casualties on both sides. Military planners were preparing for an invasion of the Japanese home islands, an operation expected to cost hundreds of thousands of American lives and perhaps millions of Japanese lives. In this context, the nuclear weapons being developed at Los Alamos took on a new significance. They were no longer just a deterrent against Nazi Germany but a potential way to end the war with Japan without the need for a costly invasion. The logic seemed clear to many involved in the project. If the bombs could demonstrate such devastating power that Japan would surrender rather than face more such attacks, they would actually save lives on both sides. But not everyone shared this logic. Some scientists, particularly those who had fled European fascism, were increasingly troubled by what they were creating. Leo Szilard, who had helped initiate the project with his letter through Einstein, now tried to stop the bomb from being used. He drafted a petition that was circulated among scientists at the Manhattan Project sites, arguing that the bomb should not be used against Japan without first demonstrating its power in an uninhabited area and giving Japan a chance to surrender. Other scientists countered that a demonstration might not be convincing, or that the Japanese might move American prisoners of war to the demonstration site, or that the project only had enough fissionable material for a very few bombs and could not afford to waste one on a demonstration. And there was the argument that after spending $2 billion and several years of work, after asking tens of thousands of people to sacrifice and keep secrets, the bomb had to be used to justify the enormous investment. Oppenheimer himself was deeply conflicted. He understood better than almost anyone the terrible power of what they were creating. He had studied Sanskrit and Hindu philosophy, had read the Bhagavad Gita in the original. Later, he would recall thinking of a line from that sacred text when he saw the first bomb explode, "Now I am become death, the destroyer of worlds." Yet he also felt the weight of responsibility to see the project through, to give the country and the military the weapon he had promised to deliver. In late June 1945, a committee of scientists, military leaders, and government officials met to discuss how the bomb should be used. They concluded that it should be used against Japan as soon as possible, without warning, and against a target that would maximize the psychological impact, a dual target, meaning both a military installation and a city with civilian population. The goal was not just to destroy military capability but to shock Japan into surrender. President Truman, who had only learned of the Manhattan Project upon Roosevelt's death in April, faced the decision of whether to authorize the use of these weapons. He was a man who had not sought the presidency, had been kept in the dark about major wartime decisions, and now found himself responsible for choices that would affect millions of lives and shape the post-war world. The weight of that responsibility was crushing, but Truman prided himself on making difficult decisions without excessive agonizing. Before any bombs could be used, they had to be tested. By July 1945, enough plutonium had been produced at Hanford for a test device and one weapon. The test was scheduled for mid-July at a remote site in southern New Mexico called Jornada del Muerto, the Journey of Death, a stretch of desert between the Rio Grande and the mountains to the east. The test device, codenamed Gadget, was assembled in a ranch house turned laboratory, then transported to the test site and hoisted to the top of a 100-foot steel tower. Instruments were placed at various distances to measure the blast's effects. Shelters were built 10,000 yards away where observers could watch in relative safety. Everything had to work perfectly the first time. There was no practice run for a nuclear explosion. Picture the scene in the hours before the test. It is the night of July 15 to 16, 1945. A thunderstorm moves across the desert, lightning illuminating the flat landscape and the distant mountains. The scientists wait in their shelters, tense with anticipation and fear. What if the bomb fails to work? What if it works too well? Fermi takes bets on whether the explosion will ignite the atmosphere, ending all life on Earth, a possibility that had been calculated to be essentially impossible, but which cannot be completely ruled out until the moment of detonation. Oppenheimer chain-smokes, unable to keep still, worrying about the weather, about whether they should postpone. General Groves paces, concerned about the political and military implications if the test fails. The countdown is delayed, then delayed again as the storm passes. Finally, as dawn approaches, the weather clears enough to proceed. At 5:29 a.m. Mountain War time, the bomb is detonated. For an instant, there is light. Light brighter than 1,000 suns, light that turns night into day, light that can be seen through closed eyelids from miles away. Then comes the heat, a wave of thermal radiation that reaches out across the desert, singeing the sparse vegetation. Then the shock wave, a wall of compressed air traveling faster than sound, rattling the observation shelters, throwing up a wave of dust as it expands outward. The fireball expands, rising on a column of superheated air, drawing up dust and debris to form the characteristic mushroom cloud that will become the symbol of the nuclear age. The cloud rises 8 miles into the stratosphere, glowing with colors never before seen on Earth, purples and greens and oranges, the light of transmuted elements, of matter transformed into energy on a scale previously seen only in stars. Those who witnessed it struggled to find words. Kenneth Bainbridge, director of the test, turned to Oppenheimer and said, "Now we are all sons of bitches." Oppenheimer himself would remember the line from the Bhagavad Gita. Others spoke of beauty and terror combined, of a sense that they had crossed a threshold that could not be uncrossed, that humanity had eaten from the tree of knowledge and could not return to innocence. The test crater was half a mile wide, the sand fused into a greenish glass that would later be called trinitite. The steel tower had vaporized completely. Instruments detected radioactivity spreading downwind, though its dangers were not fully understood at the time. The yield was estimated at about 20 kilotons, equivalent to 20,000 tons of TNT, far more powerful than any conventional weapon ever built. The news was relayed immediately to President Truman, who was at the Potsdam Conference in Germany, meeting with Stalin and Churchill to discuss the post-war settlement. Armed with the knowledge that America now possessed a working nuclear weapon, Truman's negotiating position was strengthened. Some historians argue that the successful test made the invasion of Japan unnecessary, that Japan would have surrendered within months even without the bomb due to the combined pressure of American blockade, conventional bombing, and Soviet entry into the war. Others maintain that Japan's military leadership was prepared to fight to the last citizen and that only the shock of nuclear weapons could overcome their determination. In early August, the components of 2 bombs, the untested gun-type uranium bomb Little Boy, and an implosion plutonium bomb identical to the tested device, called Fat Man, were transported to Tinian Island in the Pacific. The 509th Composite Group, specially trained for the mission, prepared for the flights. The target list had been refined through the summer. Four cities were selected as potential targets: Hiroshima, Kokura, Niigata, and Nagasaki. These were chosen because they were relatively undamaged by conventional bombing. The military wanted the effects of the nuclear weapon to be clearly distinguishable and measurable. Kyoto, Japan's ancient capital and cultural heart, was initially on the list but was removed at the insistence of Secretary of War Henry Stimson, who had honeymooned there and understood its cultural significance. On August 6, 1945, a B-29 bomber named Enola Gay, piloted by Colonel Paul Tibbets, took off from Tinian carrying Little Boy. The flight to Japan took about 6 hours. Weather planes scouted the potential targets and radioed back that Hiroshima had clear skies. At 8:15 a.m. local time, the bomb was released over the city from an altitude of 31,000 feet. Hiroshima was a city of about 350,000 people, an important military headquarters and industrial center, but also filled with civilians going about their morning routines. Some were eating breakfast, some were walking to work or school, some were already at their jobs. Air raid sirens had sounded earlier when weather planes passed over, but the all-clear had been given, and people had returned to their daily activities. The bomb fell for 43 seconds, then detonated about 2,000 feet above the city. In an instant, the center of Hiroshima ceased to exist. The fireball reached temperatures of several million degrees, vaporizing everything within a few hundred yards. People close to ground zero were burned so completely that only their shadows remained, etched onto walls by the thermal radiation that had shielded the surface behind their bodies. The blast wave that followed the light flattened buildings for a mile in every direction. Wooden structures were blown apart, their fragments becoming lethal projectiles. Even reinforced concrete buildings were severely damaged. Fires ignited across the city, from overturned cooking fires, from broken gas lines, from the thermal radiation itself, and these fires would soon merge into a firestorm that consumed much of what the initial blast had left standing. Those who survived the initial explosion found themselves in a landscape of almost incomprehensible devastation. The familiar city had been replaced by a flat plain of rubble and fire, with only a few gutted concrete buildings standing like tombstones. The injured were everywhere, people with severe burns, people impaled by flying debris, people staggering through the ruins calling for loved ones, people who appeared uninjured but who had absorbed lethal doses of radiation. Dr. Michihiko Hachiya, director of Hiroshima Communications Hospital, survived the blast and kept a detailed diary of the aftermath. He described the confusion and horror, the overwhelming number of injured, the lack of medical supplies or even intact medical facilities, the strange symptoms that began appearing in the following days: nausea, bleeding, hair loss, the signature of radiation sickness, though no one yet understood what they were seeing. The death toll from the Hiroshima bombing has never been precisely determined. Somewhere between 70,000 and 80,000 people died immediately or within the first few hours. By the end of 1945, the death toll had reached perhaps 140,000, as injuries and radiation sickness claimed more lives. In the years that followed, thousands more would die from cancers and other illnesses caused by radiation exposure. Entire families were simply gone, their homes and bodies obliterated, leaving no one to remember them or mourn their passing. The Japanese government initially struggled to understand what had happened. Communications from Hiroshima were severed. Reports from reconnaissance aircraft spoke of a city that had been destroyed by a single bomb, which seemed impossible. The military dispatched investigators, and when they reached Hiroshima, they found a scene beyond anything they had imagined. This was not the work of conventional weapons, not even the massive firebombing raids that had destroyed Tokyo and other cities earlier in the year. This was something entirely new. President Truman announced the attack in a radio address, describing the bomb as a harnessing of the basic power of the universe, and warning that, if they do not now accept our terms, they may expect a rain of ruin from the air, the like of which has never been seen on this earth. The statement was intended to shock Japan into immediate surrender, to make clear that resistance was futile in the face of such overwhelming power. But the Japanese government did not surrender. The military leadership, in particular, argued that the Americans could not possibly have many such bombs, that they should continue fighting. There was debate, confusion, and a kind of paralysis in the face of the unprecedented. The Japanese Supreme War Council met but could not reach agreement. Some members argued for immediate surrender, others for continuing the fight. 3 days later, on August 9th, a second bombing mission took off from Tinian. The primary target was Kokura, but clouds obscured the city, and after 3 passes, the bomber crew diverted to the secondary target, Nagasaki. This city was home to about 240,000 people and, ironically, had the largest Christian population in Japan, with a cathedral that was one of the finest in Asia. Fatman was dropped at 11:02 a.m. local time and detonated about 1,500 feet above the industrial valley of Nagasaki. The terrain partially shielded some areas of the city, and the bomb detonated slightly off target, but the devastation was still catastrophic. The blast destroyed about 2 square miles of the city, killed between 40,000 and 75,000 people immediately, and left tens of thousands more injured or dying. Sumateru Taniguchi, a mail carrier who was delivering letters when the bomb fell, survived with terrible burns across his back and arm. He would spend years in hospitals and became one of the Hibakusha, the bomb-affected people, who dedicated their lives to warning the world about the horror of nuclear weapons. His testimony and that of other survivors would become a powerful counterweight to the abstract calculations of military planners and strategists. Between the 2 bombings, the Soviet Union declared war on Japan and launched a massive invasion of Japanese-held Manchuria, overrunning the Japanese forces there with surprising speed. This fulfilled a promise Stalin had made at the Potsdam Conference, though the timing, just after Hiroshima, also served to ensure that the Soviets would have a role in shaping the post-war settlement in Asia. Japan now faced catastrophe from multiple directions: atomic bombs from the air, Soviet invasion from the north, continuing American conventional bombing, and a naval blockade that was strangling their economy. Even so, the Supreme War Council remained deadlocked. The military leaders could not bring themselves to accept surrender, which went against everything they had been taught about honor and duty. Emperor Hirohito, who had remained largely silent during the debates, finally intervened. In an unprecedented radio address on August 15, 1945, he announced Japan's surrender, citing a new and most cruel bomb that had given him no choice. His voice, heard by most Japanese for the first time, instructed his people to endure the unendurable and suffer what is insufferable. For many Japanese, the emperor's words were the only thing that could have overcome the military's determination to fight on. The war was over. After 6 years of conflict that had engulfed the globe, after tens of millions of deaths, after the Holocaust and the firebombings and the island-hopping campaigns across the Pacific, it ended not with the climactic battle but with the capitulation of an entire nation in the face of a weapon that rendered conventional military strength obsolete. The atomic bombings of Hiroshima and Nagasaki remain among the most controversial actions in military history. To this day, historians and ethicists debate whether they were necessary, whether they saved more lives than they took, whether there were alternatives that were not adequately explored. Some argue that the bombings were justified as the quickest way to end the war and avoid the massive casualties that would have resulted from an invasion. Others contend that Japan was already defeated and would have surrendered within weeks or months, making the atomic bombings unnecessary acts of terror against civilian populations. What is undeniable is that the bombings introduced a new element into warfare and international relations, something that would fundamentally alter how nations thought about conflict, power, and survival. The atomic bomb was not just a more powerful weapon but a weapon of a different kind, one that threatened the very existence of civilization itself if used in any future conflict between major powers. In the immediate aftermath of Japan's surrender, the world began to grapple with the implications of nuclear weapons. The Manhattan Project was revealed to the public, and suddenly everyone knew that atomic energy was real, that Einstein's equation E equals mc squared had practical applications, that matter could be converted to energy with terrifying efficiency. The scientists who had built the bomb found themselves in an unexpected position. Many had assumed that their work would end with the war, that they would return to pure research and academic life. Instead, they found themselves thrust into political debates about the future of atomic energy, about international control of nuclear weapons, about the role of science in society. The Frank Report, written by a committee of Manhattan Project scientists in June 1945 but suppressed until after the war, had argued against using the bomb on cities without warning. It predicted that doing so would start an arms race, would create international fear and hatred of the United States, and would make future international control of atomic energy more difficult. Many of the scientists felt that their warnings had been ignored, that the political and military leadership had rushed to use the bombs without adequately considering the long-term consequences. Oppenheimer, in particular, found himself haunted by what he had helped create. In a meeting with President Truman shortly after the war, he told the president that he felt he had blood on his hands. Truman, angered by what he saw as weakness and sentimentality, reportedly responded, "Never mind. It'll all come out in the wash," and later told an aide that he never wanted to see the crybaby scientist again. The exchange highlighted a fundamental divide between those who had to make the political and military decisions and those who had provided the technical means to carry them out. But Oppenheimer and others threw themselves into efforts to prevent nuclear weapons from being used again. They advocated for international control of atomic energy, for sharing nuclear knowledge with other nations to prevent an arms race, for civilian rather than military control of nuclear research in the United States. The Acheson-Lilienthal Report of 1946 proposed an international atomic development authority that would control all dangerous nuclear activities worldwide, a vision of global cooperation that was idealistic but also reflected genuine fear about what would happen if multiple nations developed nuclear arsenals. These hopes were quickly dashed by the emerging Cold War. The wartime alliance between the United States and the Soviet Union had always been uncomfortable, based on the practical necessity of defeating Nazi Germany rather than on any fundamental agreement about political ideology or post-war goals. With Germany defeated, the tensions that had been papered over during the war erupted into open conflict, though a conflict fought through proxies, espionage, and political maneuvering rather than direct military confrontation. The Soviet Union, under Joseph Stalin, was deeply suspicious of American intentions and felt surrounded by hostile powers. Stalin had lost more than 20 million citizens in the war against Germany, and he was determined to create a buffer zone of friendly states in Eastern Europe to prevent any future invasion. He was also acutely aware that the United States possessed atomic weapons while the Soviet Union did not, creating a dangerous imbalance of power. The Americans, for their part, saw Soviet actions in Eastern Europe. The installation of communist governments, the suppression of non-communist political movements, the incorporation of the Baltic states, as evidence of aggressive expansionism that threatened to spread communist ideology worldwide. The mutual suspicion and fear created a self-fulfilling prophecy, where each side's defensive measures appeared aggressive to the other, leading to escalation and counter-escalation. In this context, the idea of international control of atomic energy became politically impossible. The United States was not willing to give up its nuclear monopoly without ironclad guarantees of Soviet compliance, while the Soviet Union was not willing to accept any control system that would leave the U.S. with superior knowledge and capabilities. The Baruch Plan, presented to the United Nations in 1946, would have placed all nuclear activities under international control, but it required the Soviet Union to submit to intrusive inspections and to accept a system where they could be outvoted. Stalin rejected it as designed to perpetuate American nuclear dominance. Meanwhile, the Soviet Union was working frantically to develop its own atomic bomb. Stalin had ordered the project to begin even before the war ended, and after Hiroshima, he made it the highest national priority. The Soviet program benefited enormously from espionage. Spies within the Manhattan Project, most notably Klaus Fuchs, a German-born physicist who had worked at Los Alamos, had provided detailed information about bomb design, saving the Soviets years of research and development. On August 29, 1949, the Soviet Union detonated its first atomic bomb at a test site in Kazakhstan. The blast was detected by American aircraft equipped with instruments to sample the upper atmosphere for radioactive particles. When the data was analyzed, it became clear that the Soviets had achieved what many in the US had believed would take them years longer to accomplish. The end of the American nuclear monopoly sent shock waves through American society and politics. Suddenly, the sense of security that the bomb had provided was gone. The United States was vulnerable to atomic attack, and there was no defense against such weapons. Cities could be destroyed in minutes, and there would be no warning, no time to evacuate, no meaningful civil defense. This realization led to a debate about whether to develop even more powerful weapons. The atomic bombs dropped on Japan derived their energy from fission, the splitting of uranium or plutonium nuclei. But physicists had long known that another nuclear process was possible: fusion, the combining of light nuclei like hydrogen into heavier ones, releasing even more energy. This was the process that powered the sun and stars, and if it could be achieved in a weapon, the explosive yield would be essentially unlimited, measured not in kilotons but in megatons, millions of tons of TNT equivalent. Edward Teller, a Hungarian-born physicist who had worked on the Manhattan Project, became the leading advocate for developing a hydrogen bomb, also called a thermonuclear weapon or super. He argued that the Soviet Union would inevitably develop such weapons and that America needed to maintain its technological lead. Others, including Oppenheimer, opposed the development of the H-bomb on both technical and moral grounds, arguing that it was unnecessary for national security and that its enormous destructive power would make it unusable except in a war of genocide. President Truman, faced with the Soviet atomic test and under pressure from military and political advisors, authorized development of the hydrogen bomb in January 1950. The decision was made easier by the deteriorating international situation. Just months later, North Korea, backed by the Soviet Union and Communist China, would invade South Korea, leading to a war that would kill millions and cement the division between communist and non-communist blocs. The technical challenges of building a hydrogen bomb proved formidable. A fission bomb could serve as a trigger, providing the temperatures and pressures needed to initiate fusion, but getting the fusion reaction to propagate efficiently required innovations in bomb design. It was not until 1952 that the United States successfully tested a thermonuclear device, a massive experimental apparatus called Ivy Mike, weighing over 80 tons and requiring an entire building to house its cryogenic refrigeration system for the liquid deuterium fuel. The explosion, at Enewetak Atoll in the Pacific, vaporized the island on which it sat, creating a crater 6,000 feet wide and 160 feet deep. The yield was 10.4 megatons, more than 500 times the power of the Nagasaki bomb. The mushroom cloud rose to 130,000 feet, well into the stratosphere. Radioactive fallout contaminated islands hundreds of miles downwind. Less than a year later, the Soviet Union tested its own thermonuclear device, again demonstrating that the Americans' technological lead was shorter than expected. The nuclear arms race, which had begun with the first Soviet atomic test, now accelerated dramatically. Both superpowers began producing nuclear weapons in vast quantities, developing missiles and bombers to deliver them, building radar networks and early warning systems to detect incoming attacks. Picture the world of the 1950s and early 1960s. A world living under the shadow of potential annihilation, where schoolchildren practiced duck-and-cover drills, where families built backyard fallout shelters, where civil defense authorities published guides on how to survive nuclear war that were simultaneously earnest and darkly absurd. The guidance to hide under your desk or cover yourself with a newspaper if you saw a nuclear flash became a symbol of the profound anxiety of the age, the sense that civilization itself hung by the thinnest of threads. The nuclear arsenals grew to staggering sizes. At their peak in the mid-1980s, the United States and Soviet Union together possessed over 60,000 nuclear warheads, with explosive yields ranging from a fraction of a kiloton to 50 megatons or more. This was enough destructive power to destroy human civilization many times over, leading strategists to speak grimly of overkill and the ability to bounce the rubble. The strategy that emerged to prevent these weapons from being used was called deterrence, and specifically mutual assured destruction, which came to be known by the grimly appropriate acronym MAD. The logic was simple but terrifying. If both sides had enough nuclear weapons to destroy each other even after absorbing a first strike, then neither side would dare to launch such an attack, knowing that it would lead to their own destruction. Peace would be maintained not through goodwill or international cooperation but through the shared certainty of mutual suicide. This strategy required maintaining a credible second strike capability, the ability to retaliate even after your own country had been devastated by a surprise attack. To achieve this, both superpowers developed what became known as a nuclear triad: land-based intercontinental ballistic missiles in hardened silos, strategic bombers on constant alert, and ballistic missile submarines hidden in the depths of the oceans. An enemy could not destroy all three legs of the triad simultaneously, ensuring that retaliation would be inevitable. The submarines were perhaps the most chilling element of this system. These vessels, armed with missiles carrying multiple nuclear warheads, would patrol beneath the waves for months at a time, maintaining radio silence, completely isolated from the world. Their crews understood that if they ever received orders to launch their missiles, it would mean that their homeland had already been destroyed, their families likely dead, civilization as they knew it ended. Yet they maintained their vigilance, practicing their launch procedures, ready to execute their terrible duty if the order came. The closest the world came to nuclear war was probably during the Cuban Missile Crisis of October 1962. The Soviet Union, seeking to counter American missiles in Turkey and to protect their ally Fidel Castro's communist regime in Cuba, secretly deployed nuclear-armed ballistic missiles to the island, just 90 miles from Florida. When American reconnaissance aircraft discovered the missiles, President John F. Kennedy faced an agonizing decision. A military strike to destroy the missiles risked escalation to full nuclear war. A blockade, which Kennedy called a quarantine to avoid the legal implications of an act of war, might buy time for negotiation but could provoke the Soviets to force their way through. Doing nothing was politically impossible and would leave American cities vulnerable to missiles with only a few minutes warning time. For 13 days, the world held its breath as the crisis unfolded. Nuclear-armed American bombers circled in the air, ready to strike Soviet targets. Soviet submarines prowled the Caribbean, some carrying nuclear-armed torpedoes, harassed by American destroyers. In several instances, submarine commanders were authorized to use nuclear weapons if they lost contact with Moscow and came under attack, and they came very close to doing so. Picture those submarine commanders, deep beneath the waves, cut off from communication, under attack by depth charges, their vessels overheating, their air growing foul, having to decide whether this was the start of World War III and whether they should launch their nuclear weapons. In at least one case, on the submarine B-59, the captain and political officer wanted to launch a nuclear torpedo, and only the presence of a third officer whose authorization was needed prevented them from doing so. The world came within a single vote of nuclear war, and most people never knew how close they had come. The crisis was eventually resolved through secret negotiations. The Soviet Union agreed to remove its missiles from Cuba in exchange for an American promise not to invade Cuba and a secret agreement to remove American missiles from Turkey. Both Kennedy and Khrushchev, the Soviet leader, understood how close they had come to catastrophe, and the experience sobered them. In the aftermath of the Cuban Missile Crisis, several important changes occurred. A direct communication line, the famous hotline, was established between Washington and Moscow to prevent future crises from escalating due to misunderstanding or lack of communication. Negotiations began on arms control treaties to limit the nuclear arms race. The Limited Test Ban Treaty of 1963 prohibited nuclear weapons tests in the atmosphere, underwater, and in space, reducing radioactive fallout and establishing the principle that nuclear weapons could be controlled through international agreement. But the fundamental dynamics of the Cold War continued. Both sides kept building more weapons, developing more sophisticated delivery systems, finding new ways to threaten each other. The doctrine of deterrence remained dominant, and generations grew up knowing that their lives could end in nuclear fire at any moment, with no warning and no possibility of protection. Other nations, meanwhile, sought to acquire nuclear weapons. Britain had developed its own atomic bomb by 1952, wanting to maintain its status as a great power and not wanting to be entirely dependent on American protection. France followed in 1960, under Charles de Gaulle's leadership, seeing nuclear weapons as essential to national sovereignty and international prestige. China, after a bitter split with the Soviet Union, tested its first atomic bomb in 1964, becoming the fifth acknowledged nuclear power. Each new addition to the nuclear club raised concerns about proliferation, the spread of nuclear weapons to more and more countries. If every nation that felt threatened sought nuclear weapons for protection, where would it end? Would there be dozens of nuclear powers, making it increasingly likely that somewhere, sometime, nuclear weapons would be used, whether through miscalculation, accident, or deliberate aggression? To address this concern, the Nuclear Non-Proliferation Treaty was negotiated in the late 1960s. Under this treaty, nations that did not have nuclear weapons agreed not to acquire them, while the nuclear weapon states agreed to work toward eventual disarmament. The treaty also recognized the right of all nations to develop nuclear energy for peaceful purposes, with safeguards to prevent diversion of nuclear materials to weapons programs. The NPT was a compromise, and many non-nuclear states resented what they saw as a double standard. The nuclear powers could keep their weapons while denying them to others. Some nations refused to sign, including Israel, India, and Pakistan, all of which would eventually develop nuclear weapons. Others signed but later withdrew or violated their commitments. Still, the treaty established an international norm against nuclear proliferation and created mechanisms for monitoring nuclear activities. The existence of nuclear weapons also spurred development of nuclear energy for electricity generation. The same nuclear reactions that powered bombs could be harnessed in controlled conditions to produce heat, which could generate steam to drive turbines and produce electricity. The first nuclear power plants were built in the 1950s, and proponents spoke enthusiastically of electricity, too cheap to meter, of nuclear-powered ships and aircraft, of a future where atomic energy would free humanity from dependence on fossil fuels. The reality proved more complex. Nuclear power plants were expensive to build and raised concerns about safety and waste disposal. The radioactive waste from nuclear reactors remains dangerous for thousands of years, and no nation has yet implemented a fully satisfactory solution for its long-term storage. Accidents at nuclear plants, most notably at 3 Mile Island in 1979, Chernobyl in 1986, and Fukushima in 2011, demonstrated that despite multiple safety systems, things could still go catastrophically wrong. The connection between nuclear power and nuclear weapons, the so-called dual-use nature of nuclear technology, also complicated efforts to prevent proliferation. The same enrichment facilities that produce fuel for reactors can, with further processing, produce weapons-grade uranium. The same reactors that generate electricity also produce plutonium that could potentially be extracted and used in weapons. Nations seeking nuclear weapons often claimed they were only developing peaceful nuclear energy, making it difficult to distinguish legitimate programs from covert weapons development. Throughout the 1970s and 1980s, the nuclear arms race continued despite periodic efforts at arms control. The Strategic Arms Limitation talks produced treaties that capped the number of strategic delivery systems each side could have, but these were partial measures that did not stop the development of new weapons or reverse the buildup. Both superpowers deployed multiple independently targetable reentry vehicles, MIRVs, which allowed a single missile to carry multiple warheads that could hit separate targets, effectively multiplying the number of weapons without violating treaty limits on missiles. New technologies raised new fears. Cruise missiles, small, pilotless aircraft that could fly at low altitude beneath radar coverage, were difficult to detect and verify, complicating arms control. The Strategic Defense Initiative, proposed by President Reagan in 1983, envisioned using lasers and other advanced weapons to shoot down incoming missiles, potentially negating the other side's deterrent. Critics called it Star Wars and argued it would destabilize deterrence by making one side feel vulnerable, possibly triggering a first strike in a crisis. The Soviet Union, meanwhile, was straining under the economic burden of the arms race. Their economy was inefficient and technologically backward compared to the West, and the enormous resources devoted to military competition left little for consumer goods or infrastructure investment. When Mikhail Gorbachev came to power in 1985, he recognized that the Soviet system could not continue as it had, and he initiated reforms, glasnost, openness, and perestroika, restructuring, intended to revitalize Soviet society. Gorbachev also proved willing to engage seriously on arms control. The Intermediate Range Nuclear Forces Treaty of 1987 was the first agreement to actually reduce nuclear weapons, eliminating an entire class of missiles from Europe. It included unprecedented verification measures, allowing each side to inspect the other's facilities to confirm compliance. For the first time, the arms race seemed to be reversing. Then, with stunning speed, the Cold War ended. Communist regimes across Eastern Europe collapsed in 1989. The Berlin Wall, symbol of European division, was torn down by jubilant crowds. Germany reunified. The Soviet Union itself dissolved in 1991, breaking into 15 independent nations. The ideological struggle that had shaped global politics for nearly half a century simply evaporated, leaving many people bewildered by the sudden change. The end of the Cold War raised hopes that the nuclear threat might fade as well. The United States and Russia negotiated further treaties reducing their arsenals. Nuclear weapons were removed from former Soviet republics like Ukraine, Kazakhstan, and Belarus. The fear of imminent nuclear war that had haunted the world for decades seemed to recede. But nuclear weapons did not disappear. Even with reductions, the United States and Russia each retained thousands of warheads. Other nuclear powers, Britain, France, China, maintained their arsenals. And new concerns emerged. India and Pakistan both openly tested nuclear weapons in 1998, creating a nuclear standoff in South Asia where territorial disputes and historical animosities made the threat of nuclear war very real. North Korea developed nuclear weapons despite international opposition, creating a security crisis in East Asia. Iran's nuclear program, though officially for peaceful purposes, raised concerns that another volatile region might see nuclear proliferation. Perhaps most worrying was the possibility of nuclear terrorism, that a terrorist group might acquire nuclear materials or even a working weapon and use it to devastating effect. The security of nuclear materials, particularly in the former Soviet Union where thousands of warheads and large quantities of weapons-grade materials existed, became a major international concern. Programs were established to improve security and accounting, to employ former weapons scientists in peaceful work to prevent the loose nukes problem from becoming catastrophic. The nuclear bomb had changed not just warfare but the entire framework of international relations. The fundamental fact that nuclear-armed nations cannot fight each other directly without risking their own destruction has created what some call the long peace, the absence of direct war between major powers since 1945, the longest such period in modern history. But this peace rests on a foundation of terror, on the threat of annihilation held permanently over humanity's head. Nuclear weapons have also changed how we think about science and its relationship to society. The Manhattan Project demonstrated that basic scientific research could have enormous practical consequences, that discoveries made in pursuit of pure knowledge could reshape the world in fundamental ways. It raised questions about the responsibility of scientists for the applications of their work, about whether there are some things we should choose not to know or not to build even if we have the technical capacity. Many of the Manhattan Project scientists spent the rest of their lives wrestling with these questions. Oppenheimer, stripped of his security clearance in 1954 after a bitter political fight over his opposition to the hydrogen bomb, became a symbol of the scientist who creates something terrible and then struggles with the moral implications. His famous quote, "In some sort of crude sense, which no vulgar ism can quite extinguish, the physicists have known sin, and this is a knowledge which they cannot lose," captures the sense that the act of creation had moral weight, that one could not simply create and then wash one's hands of the consequences. Others took different lessons. Teller remained convinced throughout his life that the hydrogen bomb was necessary, that American technological superiority was essential to preventing Soviet dominance, that scientists had a duty to provide their country with the most effective weapons possible. The debate between these positions continues to this day, reflected in arguments about dual-use research in biology and artificial intelligence, about whether scientists can or should try to control the applications of their discoveries. The bomb also changed how we think about technology and progress. Before Hiroshima, technology was generally seen as beneficial, as improving human life and expanding human capability. The atomic bomb was the first technology whose primary purpose was destruction on a civilization-ending scale. It demonstrated that human cleverness had outpaced human wisdom, that we could build things we could not safely control, that progress in one dimension did not necessarily mean progress in others. This realization contributed to a broader questioning of technological optimism that characterized much of the late 20th century. The environmental movement, for instance, grew partly from the awareness that nuclear fallout from atmospheric testing was contaminating the entire planet, that strontium-90 from bomb tests was showing up in children's teeth and mother's milk everywhere on Earth. If nuclear technology could have such far-reaching unintended consequences, what other technologies might be causing hidden harm? Yet the same nuclear physics that enabled the bomb also gave us nuclear medicine, with radioactive isotopes used to diagnose and treat cancer and other diseases. It gave us methods for dating ancient artifacts and understanding Earth's history. It provided insights into the nature of matter and energy that are fundamental to our modern understanding of the universe. The knowledge itself was neutral, what mattered was how it was applied. In the decades since Hiroshima, we have lived in what might be called the nuclear age, a period defined by the existence of weapons capable of ending human civilization. This has given us a strange sort of wisdom, born of necessity. We know that total war between major powers is no longer a viable option. We know that some conflicts cannot be won in any meaningful sense, that there are no longer any safe distances in a connected world, that we share a common fate whether we like it or not. This knowledge has slowly, imperfectly, shaped international institutions and norms. The United Nations, for all its limitations, represents an attempt to manage international conflict through dialogue rather than war. Arms control treaties, even when imperfectly enforced, establish the principle that nations can limit their own military power through mutual agreement. The norm against the use of nuclear weapons, the nuclear taboo, as some scholars call it, has held for over 75 years, suggesting that even in extremis, even when conventional wars have been fought with terrible ferocity, there remains a widespread understanding that crossing the nuclear threshold would be catastrophically wrong. But this taboo is fragile, and it depends on continued vigilance and good fortune. There have been numerous close calls beyond the Cuban Missile Crisis, times when technical errors, miscommunications, or individual decisions by officers in the field could have led to nuclear weapons being used. In 1983, a Soviet early warning system mistakenly detected incoming American missiles, and only the skepticism of the duty officer, who reasoned that the U.S. would not launch such a small attack, prevented a retaliatory strike. In 1995, a Norwegian research rocket triggered Russian early warning systems, and President Yeltsin had his nuclear briefcase opened and was minutes from ordering retaliation before the mistake was identified. These incidents remind us that we have been lucky, that the systems we trust to prevent nuclear war are fallible, that the human beings operating these systems can make mistakes, that the margins for error are terrifyingly thin. They remind us that deterrence, for all its strategic logic, depends on clear communication, rational decision-making, and the absence of accidents or misunderstandings, conditions that cannot be guaranteed, especially in times of crisis when tensions are high and decision time is measured in minutes. The nuclear age has also given us a particular kind of artistic and cultural production, the literature and film and music that grapples with the possibility of nuclear war. From Nevil Shute's On the Beach to Stanley Kubrick's Dr. Strangelove to countless other works, artists have tried to help us understand what nuclear war would mean, to make concrete and real something that is almost too large to comprehend. These works serve a vital function, keeping the danger present in our minds, preventing us from becoming complacent or forgetting what is at stake. Consider the Hibakusha, the survivors of Hiroshima and Nagasaki, many of whom dedicated their lives to testifying about what they experienced, traveling the world to speak at schools and conferences, showing their scars and sharing their stories. They understood that their suffering had meaning only if it prevented future use of nuclear weapons, that their memories could serve as a warning to future generations. As they age and pass away, the youngest survivors are now in their late 70s or 80s. We lose living connections to the only nuclear attacks in history, and the question of how to preserve their testimony, how to keep that knowledge alive, becomes increasingly urgent. Looking at where we are today, more than 75 years after Trinity, the nuclear landscape is complex. The total number of nuclear weapons has decreased dramatically from Cold War peaks, from over 60,000 to perhaps 13,000 today. But many of the remaining weapons are more powerful and more sophisticated than their predecessors. The relations between nuclear powers are in some ways more stable than during the Cold War, but in other ways more complex and unpredictable. Russia and the United States still maintain the majority of the world's nuclear weapons, and relations between them have deteriorated in recent years over issues like Ukraine, election interference, and arms control treaty violations. China is modernizing and expanding its nuclear arsenal, though it remains much smaller than those of Russia, and the U.S. North Korea continues to develop nuclear weapons and long-range missiles despite international sanctions. The Iran nuclear deal, which had placed limits on Iran's nuclear program in exchange for sanctions relief, has been undermined, leaving that program's future uncertain. New technologies are also complicating the nuclear equation. Cyber weapons could potentially be used to disable nuclear command and control systems. Hypersonic missiles, which travel at speeds greater than Mach 5, could evade current missile defenses and dramatically reduce warning times. Artificial intelligence might be integrated into nuclear decision-making systems, raising questions about whether machines should ever have a role in decisions about nuclear weapons use. At the same time, the infrastructure that supports nuclear weapons is aging. In the United States, many warheads and delivery systems date from the Cold War era and are being maintained long past their intended service lives. Russia faces similar challenges. Both nations are undertaking expensive modernization programs, effectively creating new generations of nuclear weapons rather than phasing out the old ones. The question of what to do about nuclear weapons remains unresolved. Some advocate for complete nuclear disarmament, arguing that as long as these weapons exist, they pose an unacceptable risk to human survival. The Treaty on the Prohibition of Nuclear Weapons, adopted by the United Nations in 2017 and entered into force in 2021, represents this abolitionist position. However, none of the nuclear weapon states have signed this treaty, and they argue that in a world of competing nations and security threats, unilateral disarmament would be dangerously naive. Others argue for maintaining deterrence but reducing arsenals to minimal levels, just enough weapons to ensure that any attacker would face unacceptable retaliation, but not the massive overkill of Cold War arsenals. This minimum deterrence position seeks a middle ground between the abolitionist vision and the current situation. Still others believe that nuclear weapons have actually prevented major wars and that carefully managed nuclear deterrence, perhaps extended to cover additional countries through alliances, provides the best security in an imperfect world. They point to the long peace between major powers as evidence that deterrence works. Each position has its logic and its risks. What is clear is that the question of how to live with nuclear weapons, or how to live without them, remains one of the most important challenges facing humanity. We have created something that we cannot uncreate. The knowledge of how to build nuclear weapons cannot be erased. Even if every weapon were dismantled tomorrow, the knowledge would remain, and in any future conflict, nations would race to rebuild them. Perhaps the deepest change that the nuclear bomb brought about is in how we understand our own nature and our place in the universe. For most of human history, we could destroy individuals, communities, even civilizations, but the world itself, the Earth and the biosphere, would endure. Life would continue, humanity would survive somewhere even if entire regions were devastated. Nuclear weapons changed that calculation. For the first time, we possessed the means to destroy ourselves completely, to render the Earth uninhabitable, to end the human story. We had become, in a very real sense, capable of cosmic suicide. This knowledge cannot help but affect how we see ourselves, as a species that had achieved enormous power but had not necessarily achieved the wisdom to use that power responsibly. Carl Sagan, the astronomer and science communicator, spoke of the Earth as a pale blue dot, a tiny world suspended in a sunbeam, the only home we have ever known. Looking at our planet from space, as the Apollo astronauts did, brings a visceral understanding of its fragility and uniqueness. The nuclear bomb, in a paradoxical way, has reinforced this understanding. It has shown us that we could destroy this pale blue dot, this small and precious world, and in doing so has perhaps helped us appreciate what we would lose. There is a concept in psychology called terror management theory, which holds that much of human behavior is driven by the need to cope with the awareness of our own mortality. We build monuments and institutions, create art and literature, join movements and communities, all in an effort to transcend our individual mortality through legacy and meaning. The nuclear bomb has given us a collective version of this mortality, not just individual death, which is inevitable, but species death, which is preventable but possible. How we respond to this collective mortality awareness may define our future. Do we retreat into tribalism and nationalism, each group seeking security through strength, building walls and weapons to protect what is ours? Do we recognize our common vulnerability and work toward global cooperation, understanding that in the nuclear age, security cannot be achieved in isolation? Do we simply become numb to the threat, pushing it to the back of our minds and hoping that luck will continue to hold? These are not merely abstract questions. They play out in real policy decisions. About whether to fund missile defense systems or arms control verification, about whether to support international institutions or pursue national interests unilaterally, about whether to invest in diplomacy or military capability. They shape how we educate the next generation, what stories we tell about who we are and what we value. The scientists who built the first atomic bomb often said they were simply doing what scientists do, pushing the boundaries of knowledge, solving interesting technical problems, responding to the challenges of their time. But they also recognized, most of them, that they had crossed a threshold, that there was a before and an after, and that the after was fundamentally different from anything that had come before. Leo Szilard, who had helped initiate the Manhattan Project and then tried to prevent the bomb from being used on cities, once said that if he could do it over, he would become a biologist rather than a physicist. He felt that physics had been too successful, that it had given humanity powers we were not ready for. In his later years, he actually did turn to biology, working on problems of molecular biology and aging, perhaps seeking a kind of redemption through contribution to life rather than to death. Many of the Manhattan Project scientists felt a similar need to atone or to redirect their talents. Some became peace activists, some worked on nuclear arms control, some turned to other fields of science that seemed more purely beneficial. There was a sense among many of them that they bore a special responsibility, that having unleashed nuclear energy into the world, they had an obligation to help manage its consequences. But others rejected this narrative of guilt and atonement. They argued that scientific discovery was inevitable, that if they had not built the bomb, someone else would have, perhaps the Nazis or the Soviets. They pointed out that the war was real, the threat was real, and the bomb had ended the war and perhaps prevented a Soviet expansion across Europe. They insisted that moral responsibility belonged to political leaders who decided how weapons would be used, not to scientists who made them possible. This debate about responsibility continues in different forms today. When technologists develop artificial intelligence systems that might have military applications, when biologists conduct research that could be used to create new pathogens, when engineers build systems that could be used for surveillance or control, they face versions of the same questions that confronted the Manhattan Project scientists. Can you separate the creation of knowledge from its applications? Should scientists refuse to work on dual-use technologies that could be used for harm as well as good? Who bears responsibility when a technology is misused? There are no easy answers, but the nuclear bomb provides a case study we can learn from. It shows us that knowledge, once created, spreads and cannot be contained forever. It shows us that technological capability does not necessarily bring wisdom or security. It shows us that the time lag between scientific discovery and its world-changing applications can be measured in years or even months, leaving little time for society to adapt. The bomb also teaches us about the nature of secrecy and democracy. The Manhattan Project was conducted in secrecy, hidden from most of the American public and their elected representatives. This secrecy was justified as necessary for national security, to prevent enemy intelligence from learning about the project. But it also meant that one of the most consequential decisions in human history, whether to develop and use nuclear weapons, was made by a small group of people without democratic input or oversight. After the war, debates raged about whether nuclear weapons should remain under military control or be placed under civilian authority, about whether nuclear information should be shared with allies or kept secret, about how much the public should be told about nuclear testing and its effects. These debates established patterns that continue today in arguments about government surveillance, about classified military programs, about the balance between security and transparency. The nuclear age has taught us that some secrets cannot be kept permanently, but also that some information is genuinely dangerous. The technical details of how to build a nuclear weapon are, in principle, available in physics textbooks and declassified documents, but certain specific information, about how to machine plutonium cores, about the design of modern warheads, about the vulnerabilities of command and control systems, remains classified because its disclosure could make nuclear terrorism or nuclear war more likely. Walking this line between openness and security, between the democratic principle that citizens should know what their government is doing and the security principle that some information must be protected, remains one of the enduring challenges of the nuclear age. It is a tension without a perfect resolution, requiring constant judgment and adjustment. The environmental legacy of nuclear weapons is another dimension of how they changed everything. The atmospheric testing that occurred from the 1940s through the early 1960s spread radioactive fallout around the entire planet. Strontium-90 and cesium-137, products of nuclear fission, entered the global ecosystem, were absorbed by plants, concentrated in food chains, and ended up in human bodies everywhere on Earth. This was perhaps the first truly global pollution, affecting people in countries that had never tested nuclear weapons and had no nuclear programs of their own. It contributed to a growing awareness that we live in an interconnected world, that actions in one place can have consequences everywhere, that there is no way to which we can throw our waste. The environmental movement's growth in the 1960s and 1970s owes something to this awareness, which had been made visceral by the presence of bomb-produced radioactivity in every human body. The test sites themselves remain contaminated. The Nevada test site, where the United States conducted over 900 nuclear tests, is a federal facility where large areas will remain too radioactive for normal use for thousands of years. Bikini Atoll, the site of 23 American nuclear tests in the 1940s and 1950s, remains largely uninhabitable despite decades of natural decay of radioactivity. The Semipalatinsk test site in Kazakhstan, where the Soviet Union conducted hundreds of tests, left a legacy of environmental contamination and health problems in nearby populations. Even the production facilities for nuclear weapons have created lasting environmental problems. The Hanford site in Washington state, where plutonium was produced for the Manhattan Project and throughout the Cold War, is now one of the most contaminated places in the United States, with millions of gallons of radioactive waste stored in aging tanks, some of which have leaked into the ground and contaminated groundwater. Cleanup costs are estimated in the tens of billions of dollars, and the work will take decades. In Russia, the situation is even worse. The Mayak facility in the Ural Mountains, a major plutonium production site, experienced a catastrophic accident in 1957 when a tank of radioactive waste exploded, contaminating a vast area. For decades, radioactive waste from Mayak was dumped directly into local rivers, and the Teka River became one of the most radioactive places on Earth. The full extent of contamination was kept secret during the Soviet era, and only now are the health effects on local populations being fully documented. These environmental legacies will persist for generations, a physical reminder of the nuclear age that will remain long after the geopolitical circumstances that created nuclear weapons have passed. They represent a debt that we are passing to our descendants, who will have to manage radioactive materials they had no part in creating for purposes they may not understand or value. Yet for all the darkness in the story of nuclear weapons, there are also threads of hope, moments when humanity has stepped back from the brink, when wisdom has prevailed over fear or aggression, when cooperation has overcome competition. The Cuban Missile Crisis ended not in war but in negotiation. The Nuclear Non-Proliferation Treaty, for all its limitations, has been signed by most nations and has helped prevent the spread of nuclear weapons to dozens of countries that might otherwise have pursued them. The Comprehensive Nuclear Test Ban Treaty, though not yet in force, has established a de facto moratorium on nuclear testing that has held for most nations for over 2 decades. The dramatic reductions in nuclear arsenals since the Cold War ended represent a genuine achievement, the result of patient diplomacy and mutual recognition that security does not require weapons numbered in the tens of thousands. The dismantlement of nuclear weapons in Ukraine, Kazakhstan, and Belarus after the Soviet Union's collapse showed that nations can choose to give up nuclear weapons when conditions are right, that the nuclear path is not inevitably one way. Scientists from former adversaries now work together on projects ranging from nuclear security to fusion energy research. The International Atomic Energy Agency, despite its limitations, provides a forum for cooperation and verification that helps maintain trust. Civil society organizations continue to press for nuclear disarmament, keeping the issue alive in public consciousness even when governments are reluctant to act. And perhaps most importantly, we have learned. We have learned that nuclear weapons are different in kind from other weapons, that their use would cross a moral and practical threshold with consequences beyond calculation. We have learned that security in the nuclear age must be mutual, that one nation's absolute security means another's absolute vulnerability, and that such imbalances cannot be stable. We have learned that arms races are expensive, dangerous, and ultimately futile, that true strength lies in knowing when and how to exercise restraint. These lessons have been hard-won, purchased with fear and near disasters and the constant weight of living under the nuclear shadow. But they are real, and they have been incorporated, however imperfectly, into the fabric of international relations. The nuclear taboo holds. The mechanisms for dialogue and arms control exist. The understanding that we share a common fate has, to some degree, penetrated into policy and consciousness. As we move deeper into the 21st century, we carry this knowledge with us, the knowledge of what we are capable of, both for creation and destruction. The same cleverness that unlocked the atom's secrets has given us technologies that would seem magical to earlier generations. We communicate instantly across the globe. We can see into the human body without cutting it open. We have sent machines to other planets and looked back at images of Earth from billions of miles away. We are beginning to understand the genetic code of life itself and to manipulate it with precision. Each of these capabilities carries within it the same duality that nuclear energy embodies, the potential for tremendous benefit and the potential for terrible harm. The question is whether we have learned enough from the nuclear age to manage these new powers more wisely than we managed the first one. Have we developed the institutions, the wisdom, the self-restraint to use our growing capabilities responsibly? Or are we doomed to repeat the pattern, creating without fully understanding, acting without fully considering consequences, letting our fears drive us to choices we later regret? The story of the nuclear bomb is not finished. It continues every day in the decisions made in capitals around the world, in the laboratories where weapons are maintained and where new technologies are developed, in the silos and submarines where weapons wait on alert, in the diplomatic conferences where treaties are negotiated or abandoned. It continues in classrooms where young people learn about physics and history, in the memories of survivors who carry their testimony forward, in the work of activists and scientists and citizens who refuse to accept nuclear weapons as a permanent feature of human civilization. And so we find ourselves here, in this quiet moment before sleep, having traced the arc of this story from the first mysterious glow of uranium in a Paris laboratory to the vast arsenals that define our current age. We have walked through the laboratories where scientists first glimpsed the power locked within the atom, stood in the desert dawn of Trinity where that power was first unleashed, witnessed the terrible light over Hiroshima and Nagasaki, felt the chill of the Cold War when the world balanced on the knife edge of annihilation, and surveyed the complex, uncertain landscape of our present moment. The nuclear bomb changed everything, as we said at the beginning of this journey. It changed warfare, making total war between major powers suicidal rather than merely costly. It changed international relations, creating interdependencies and vulnerabilities that had never existed before. It changed how we think about science and responsibility, about knowledge and power, about humanity's relationship with technology. And perhaps most profoundly, it changed how we see ourselves, no longer masters of a world that would endure regardless of our actions, but rather uncertain stewards of a fragile planet that we now have the power to destroy. This knowledge is both a burden and a gift. The burden is the weight of responsibility, the awareness that we must somehow learn to live with powers we can barely control, that we must develop wisdom faster than we develop capability, that we can never again claim innocence about the consequences of our choices. The gift is the understanding that forces us to see clearly, to recognize our common humanity, to accept that we are all passengers together on this pale blue dot suspended in the sunbeam of the cosmos. In the end, the story of the nuclear bomb is a story about us, about what we can do, about what we choose to do, about the distance between those two things. It is a story still being written, its conclusion not yet determined. Whether it ends in wisdom or catastrophe, in the gradual dismantlement of nuclear arsenals or in their use, depends on choices that have not yet been made, on actions that have not yet been taken. But tonight, as you drift towards sleep, you can rest knowing that this story, for all its darkness, contains threads of light as well. The wisdom we have gained, however painfully. The restraint we have shown, however imperfectly. The understanding we have reached, however incompletely. These are real achievements, worthy of recognition, foundations on which further progress can be built. The atomic bomb was created because brilliant minds sought to understand the fundamental nature of reality, because nations felt threatened and sought security through strength, because the momentum of discovery and competition pushed forward faster than wisdom could restrain. It changed everything because it revealed both the heights of human achievement and the depths of human vulnerability, because it forced us to confront questions we would rather have avoided about power and responsibility, about survival and morality. We are all children of the nuclear age now, whether we know it or not. We live with its legacy every day, in ways both obvious and subtle. The world we inhabit, with its particular pattern of alliances and tensions, its specific configuration of risks and possibilities, was shaped fundamentally by the shadow of the mushroom cloud. Understanding this history helps us understand our present and perhaps gives us tools to shape our future more wisely. And so, dear friend, as the darkness deepens and sleep approaches, let these stories settle gently into your mind like snowfall on a winter evening. Remember that history is not simply something that happened long ago to people unlike ourselves, but rather the accumulated experience of humans much like us, facing challenges and making choices under circumstances they often did not fully control or understand. Their struggles, their achievements, their mistakes, all of these belong to our common heritage, lessons written in the book of human experience that remains forever open for those willing to read and learn. The nuclear age is our age. We did not choose to be born into it, but here we are, inheritors of both its perils and its wisdom. What we do with this inheritance, how we manage the powers we have been given, whether we can finally learn to see each other as fellow travelers rather than as threats, these questions remain open, their answers still being written in the choices we make each day.